66 million years ago, the Earth experienced one of the most cataclysmic events in its history, the KT Extinction, or Cretaceous-Paleogene extinction event, which marked the end of the dinosaurs and reshaped the trajectory of life on Earth. This mass extinction, caused by a combination of catastrophic events, eradicated nearly 75% of all species on the planet, including the non-avian dinosaurs that had dominated for over 160 million years. The extinction event not only ended the reign of the dinosaurs, but also paved the way for mammals, including humans, to rise and eventually thrive. The primary cause of the KT extinction is widely believed to be the impact of a massive asteroid or comet, estimated to be about 10 kilometers or 6 miles in diameter. This object struck the Earth near the Yucatan Peninsula in modern-day Mexico, creating the Chicxulub crater, a structure more than 180 kilometers or 112 miles in diameter. Nobody could have predicted the disaster. As they had done for more than 170 million years, dinosaurs hunted one another and ate verdant vegetation. On a typical late Cretaceous day, pterosaurs flew through the air, mosasaurs splashed in the waters, and small animals scuttled through the forest. Then, in a flash, everything changed. A piece of rock that was more than 6 miles across collided with the Yucatan Peninsula, and the jolt was like a gunshot on a planet. The world would never be the same. However, what was the actual event of the day the asteroid hit? Experts are piecing together a terrifying account of one of the deadliest days in our planet's history by examining the rock record. The Gulf of Mexico covers half of the enormous scar left by the impact, which left a crater more than 110 miles in diameter. However, the details are in the geological facts in several locations throughout the world, like the Gulf Coast, where there are indications of a huge tsunami. Within 10 hours, a massive wave ripped its way to the coast due to the power of the impact and the amount of water it displaced. What has settled out is a geologic mess, fossils of land plants in places that should have been the ocean, and ocean sand on what would have been dry land, all mixed together in a jumble of old material. These layers form a harsh border between the end of the Cretaceous and the beginning of the Paleocene, in the region of the world where the tsunami occurred. Not that the impacts were confined to the impact site. Even as far away as Argentina, the blast was sufficient to trigger geologic disturbances, including landslides and earthquakes, which in turn triggered their own tsunamis. But the heat posed a greater threat to life in the Western Hemisphere than the waves did. Tiny rock fragments and other debris were hurled high into the air as the asteroid crashed into Earth. Around the world, geologists have discovered tiny fragments known as spherules in a layer that is 1/10 of an inch deep. Geologist Doug Robertson of the University of Colorado states that the kinetic energy carried by these spherules is colossal, about 20 million megatons total, or about the energy of a 1 megaton hydrogen bomb at 6-kilometer intervals around the planet. About 40 minutes after impact, the spherules began to drop through the atmosphere 40 miles aloft, converting all that energy to heat. The entire Earth was bathed in intense infrared radiation from ballistically re-entering ejecta for several hours following the Chicxulub impact. Earth turned into a burning world. Each spherule became an incandescent torch due to the friction of falling, rapidly and drastically heating the atmosphere. The majority of dinosaurs and many other terrestrial species could not have escaped it because they were neither underground nor submerged. In some areas, the relentless blow was sufficient to ignite dried-out vegetation, which sparked wildfires, and animals trapped in the open may have perished immediately from several hours of high heat. A large portion of Cretaceous life may have been exterminated in a few hours, at least on land. The diversity of life was drastically reduced by the heat pulse and its after-effects alone. However, things ended up being far worse. Robertson and his team stated that it had a huge impact on the climate. There would have been an impact winter, with no sunlight reaching the Earth's surface for a year or so, due to the dust and soot from the impact and fires. Around the world, geologists may immediately observe this as a thin layer of soot that parallels the Cretaceous-Paleogene boundary, which separates the Cretaceous from the next epoch. A new peril now confronted the organisms that had miraculously survived the extreme heat and fires. According to Robertson, the phytoplankton base of almost all aquatic food chains would have been eliminated, and aquatic ecosystems would have completely collapsed if sunlight had been lost. Terrestrial plants were also deprived of vital sunlight for photosynthesis. Overall, in less time than a Tyrannosaurus rex's lifetime, evolution that took more than 180 million years to accumulate could have been reduced. At the end of the Cretaceous, death was swift. According to Robertson, it is challenging to conduct a damage census in part because dinosaurs receive an excessive amount of attention. As Robertson notes, pollen and plankton really paint a more nuanced picture of what transpired after the hit. However, according to the fossil record that is currently available, over 75% of all known species became extinct, and conditions for the surviving ones were most likely not good. These lucky animals were the ones who would go on to set the stage for the following 66 million years of evolutionary history. Although Robertson admits that it is logical to assume that the 25% of surviving species had near total mortality. A study and simulation was recently published in the journal American Geophysical Union, with researchers saying that when the asteroid struck Earth, it released an immense amount of energy, equivalent to billions of atomic bombs. The initial shockwave from the impact traveled outward, displacing an enormous volume of water and generating a wave taller than any natural structure on the planet today. This mega tsunami, propelled by the force of the impact and the displaced materials, surged outward from the epicenter. Such a towering wall of water would have been visible from hundreds of miles away, a manifestation of the sheer power unleashed by the asteroid's arrival. The almost 3-mile-tall wave was driven by a combination of factors unique to the Chicxulub impact. As the asteroid struck, it excavated vast quantities of rock and sediment, pushing water away from the impact site with incredible force. Simulations suggest that this displacement was not a gradual process, but an instantaneous and violent surge, creating a towering wave that radiated outward at high speeds. The sheer height of the wave, as described in the study, reflects the scale of the energy involved. This wave was not a typical tsunami, which is generated by undersea earthquakes or landslides, but an unprecedented event tied directly to the asteroid's kinetic energy and the subsequent ejection of material. While the mega tsunami itself was a singular phenomenon, the chaos it caused did not end with its initial formation. As debris from the impact was hurled into the atmosphere, it temporarily formed a dense cloud that encircled the Earth. This debris, much of it consisting of molten rock and fragmented sediments, eventually fell back to the planet's surface. As this material re-entered the atmosphere, it created additional disturbances. The heat generated by falling debris ignited wildfires across vast areas, while the physical impact of the material striking water bodies created secondary waves. These waves compounded the already tumultuous conditions, disrupting the initial mega tsunami and creating a chaotic series of smaller, yet still enormous waves. Simulations of this period suggest that the waves collided and interfered with one another, producing patterns of turbulence that persisted for hours or even days. The debris also introduced significant amounts of particulate matter and chemicals into the ocean, disrupting marine ecosystems and contributing to the mass extinction event. The effects of the mega tsunami were not confined to the immediate vicinity of the impact site. As the wave traveled across the ancient seas, it lost height but retained its destructive force, inundating coastlines thousands of miles away. Marine and coastal environments around the globe were devastated as the wave carried sediment and debris, burying ecosystems and altering the topography of the ocean floor. In addition to the direct effects of the wave, the mixing of sediments and nutrients in the oceans had far-reaching consequences. The sudden influx of material disrupted marine food chains, contributing to the collapse of ecosystems and the extinction of countless species. This disruption was a key factor in the broader environmental upheaval that characterized the KT extinction. In the previously mentioned study published in American Geophysical Union, the team analyzed geological evidence and applied cutting-edge computational models, and the researchers were able to reconstruct the sequence of events that unfolded in the minutes and hours following the asteroid's arrival. These findings not only illuminate the scale of the destruction, but also provide insights into the interconnected nature of Earth's systems. The interplay between the asteroid's impact, the mega tsunami, and the falling debris illustrates how a single event can cascade into a global catastrophe. The mega tsunami and its aftermath were just one part of the chain reaction that led to the KT extinction. The event serves as a stark reminder of the vulnerability of life on Earth to sudden, large-scale disruptions. By studying the Chicxulub impact, scientists gain a better understanding of how ecosystems respond to rapid changes, knowledge that is particularly relevant in the context of modern environmental challenges. Additionally, the study of the mega tsunami highlights the importance of planetary defense. While asteroid impacts of this magnitude are rare, their consequences are so profound that even a low probability warrants significant attention. Researchers estimate that the tsunami was up to 30,000 times more energetic than the devastating December 26, 2004 Indian Ocean tsunami, which claimed more than 230,000 lives across multiple countries. The 2004 tsunami, one of the largest and deadliest in recorded history, was driven by a massive undersea earthquake. In contrast, the Chicxulub tsunami was powered by an asteroid impact that released energy at least 100,000 times greater than the Tonga volcanic eruption, a force so colossal that it altered the Earth's geological landscape. The tsunami's energy and magnitude were unmatched. As it radiated outward from the impact site, it disturbed sediments in ocean basins halfway around the world. This immense force not only displaced and eroded existing sediments, but also deposited older materials into jumbled layers. These disruptions have left a permanent mark in the sedimentary records, serving as a geologic signature of the asteroid's catastrophic arrival. Simulations of the Chicxulub tsunami show that the wave propagated across ancient oceans at speeds comparable to modern jetliners, covering vast distances in hours. By the time the wave reached distant coastlines, it had diminished in height, but still carried enough energy to inundate shores and devastate ecosystems. Coastal regions in what are now North and South America, Europe, and Africa were likely submerged, with waves potentially reaching several hundred feet high. In open ocean basins, the tsunami's power was sufficient to stir sediments on the sea floor, disrupting stratified layers that had accumulated over millions of years. This disturbance created chaotic sedimentary deposits, including gaps where material was completely scoured away and replaced by older, deeper sediments. These anomalies in the geologic record serve as a stark reminder of the event's extraordinary reach and energy. A recent study published in Nature Geoscience revealed that the asteroid dust caused a 15-year winter that killed dinosaurs. The immediate aftermath of the asteroid impact saw temperatures drop by as much as 25 degrees in some regions. This rapid cooling disrupted weather patterns and led to the collapse of ecosystems that had thrived during the relatively stable climate of the Cretaceous period. Plants were among the first casualties of the impact winter. Deprived of sunlight, photosynthesis became impossible, and vegetation across the globe began to die off. This collapse of primary producers had a cascading effect on the food chain. Herbivorous dinosaurs, unable to find sufficient food, perished in massive numbers, and their predators followed shortly after. Marine ecosystems also suffered, as phytoplankton, the base of the oceanic food web, were similarly affected by the lack of sunlight. The study highlights that this 15-year winter was not a uniform event, but varied in severity depending on the region. High latitudes experienced the most extreme cooling, with prolonged snow and ice cover, while equatorial regions saw less dramatic temperature drops. However, the global nature of the dust. The researchers estimate that almost 2,000 gigatons of dust from crushed rock were thrown into the atmosphere, blocking the light and seriously interfering with plant photosynthesis. These discoveries were made feasible by sophisticated modeling techniques that showed that the air dust, which was more than 11 times the mass of Mount Everest, lasted for up to 15 years and created a worldwide nuclear winter, which in turn led to the demise of the dinosaurs. According to recent popular hypotheses, either soot from the resulting worldwide wildfires or sulfur from the asteroid's impact covered the sky, plunging the planet into a long, cold gloom that only a lucky few species survived. However, the present study, which used particles from an important fossil site, revived an earlier theory that the asteroid-stirred dust was the main cause of the nuclear winter. Situated 1,800 miles away from the crater, this location has produced remarkable discoveries that are thought to have been preserved in old lake sediment layers and date to the early aftermath of the asteroid impact. By incorporating this information into climate models similar to those used for current Earth assessments, the scientists came to the conclusion that dust contributed more to the mass extinction than previously thought, accounting for 75% of the material released into the atmosphere compared to 24% sulfur and 1% soot. Even after the dust began to settle and sunlight started to return, the effects of the impact lingered for decades. The cooling period was followed by a phase of rapid warming, as the massive amounts of carbon dioxide released by wildfires and the vaporized limestone at the impact site created a greenhouse effect. This rapid climate fluctuation further stressed surviving species, many of which were already on the brink of extinction. The study emphasizes that the 15-year winter was the most significant factor in the KT extinction event, as it wiped out the majority of species that could not adapt to the harsh and rapidly changing conditions. Small, burrowing mammals, capable of surviving on limited resources and tolerating colder temperatures, emerged as some of the few survivors. Their resilience during this period laid the foundation for the rise of mammals and, eventually, human evolution. The findings of the Nature Geoscience study provide a more detailed understanding of the KT extinction event and its long-term effects on Earth's climate and ecosystems. By simulating the atmospheric impact of the asteroid dust, researchers were able to quantify the severity and duration of the impact winter, offering new insights into how such catastrophic events reshape the planet. The study also underscores the interconnectedness of Earth's systems. The asteroid impact, while a singular event, triggered a cascade of effects that spanned atmospheric, oceanic, and terrestrial ecosystems.